Welcome civil engineering viewers and students. Um, uh, Today we will see about how to calculate the flexibility coefficients of simply supported beam by using conjugate beam method. So this is a beam which is simply supported at its ends. Now here you take this end as A and this end as B. Now this is the real beam which is subjected to moment M at this point. The length of the real beam is L. So the distance between the supports is L. Now here we have to draw the bending moment diagram first and divide it by flexural rigidity EA. So the bending moment diagram will be something like this. Here you draw a line. At this location you have the bending moment as M by EA. Now this triangular diagram is the bending moment diagram for the real beam. So then we will here see about what is the real meaning of flexibility coefficient. So flexibility is nothing by F equal to delta divided by P. Also you can say that flexibility is equal to theta divided by M. So this theta is related to M and delta is related to P. Now here you can see that the flexibility coefficients are represented by F11 and F21. Now I will tell you what is the meaning of the subscript 21. Here 2 represents the location where you are calculating the flexibility, and 1 represents the location of the loading. So where you have applied the load. Here the loading is not applied, here moment is applied. So you have applied moment at point 1. So this 1 denotes the location of loading and this one denotes the location where you want to calculate the flexibility coefficient. So here it is F11 and here it is F21. So this 2 represents the location and 1 represents the loading at the point where which you are applying the load. So this is the real meaning of the subscript 1 and subscript 2. So F21 represents flexibility coefficient at point 2 due to moment applied at point 1. And this F11 is flexibility coefficient at point 1 due to moment applied at 1. So this is the real meaning. And regarding conjugate beam, the support conditions are same. There is no difference between the real beam and the conjugate beam. Have the same support conditions and start evaluating the shear force. So here this is the bending moment diagram for the real beam. So M by EI diagram, bending moment diagram divided by EI. Now this is a conjugate beam. The conjugate beam, here you can see that A can be taken as A dash and the other support can be taken as B dash. The distance between these two supports is nothing but L. So this 2 supports you can imagine that they are simply supported as in the case of real beam. So real beam and conjugate beam represents the same support conditions as we see earlier in the previous videos. Now here M by EA diagram is applied as loading here as triangular loading. Now we have to calculate what is the shear force at this end A and what is the shear force at this end B. The shear force at the end A is nothing but the reaction, and shear force at the end B is the reaction at B. You understand? Now here how to calculate the reactions. So first of all you consider the point B. Summation of moment at point B is equal to 0. So you can see that RA is multiplied by L, which is equal to the moment due to the loading. So here the centroid is located at this point, which is as usual 2L by 3 from the 0 point of loading. So from this point to this point the centroidal distance is 2L by 3. So here the moment due to M by EA is, so M by EA diagram is the load diagram, so half into M by EI multiplied by L. So this represents the loading. Then you multiply it by 2L by 3. So what you get finally is, here you get RA equal to ML by 3EA. So this is equal to theta A of real beam. We have found out what is theta A of real beam. Then we have to find out RB. How will you find out RB? The total loading minus RA will give you the reaction at B. Okay, total loading is ml by 2EA. So ml by 2EA minus ml by 3EA, obviously you will be getting ml by 6EA. So here you can see that the first step is carried out and RA is being formed, and in the second step RB equal to, so how RB is calculated, total load is equal to half into m by EI into L is the total loading. So ml by 2EA minus RA. RA is nothing but ml by 3EA. So if you multiply this ml by 2EA minus ml by 3EA, you are getting ml by 6EA. Then proceeding further, you have got, this is the real beam. Previously you saw the conjugate beam, this is the real beam. So theta A of the real beam is equal to RA of the conjugate beam equal to ml by 3EA, and theta B of the real beam equal to RB of the conjugate beam equal to ml by 6EA. What is RA? RA is nothing but the total shear at the point B, and RB is the total shear at the point B. Now you have got ml by 3EA and ml by 6EA. Now how to find out the stiffness coefficient? Divide theta A by m, you get L by 3EA, that is F11, flexibility coefficient at 1 due to moment applied at 1, and theta B by m equal to L by 6EA equal to F21, that is flexibility coefficient at 0.2 due to moment applied at 0.1. So you can imagine that finally flexibility coefficients L by 3EA is F11 and L by 6EA is F21. This forms the basis for any methodology where you can remember the moment distribution method, where you apply a moment at this location, half of it is getting transferred to the other end, further end. So here if you apply a moment of 3EA theta A by L, you can see that half of it is transferred to the next point, that is farther end. So this is how we evaluate the flexibility coefficients, which has got application in so many problems, including flexibility method and moment distribution method. Thanks a lot for watching. Please subscribe the channel.